particular compounds. We talked about the bonds that held them together. We had ionic and covalent bonds. You know that coming up, we're going to have reactions. Between where we are now and before we get to our reactions, we need to talk about how we deal with compounds in the real world. Okay? And this is what we're going to talk about in terms of chemical composition. So we have a sample in our hands. How do we figure out what it is, and how do we describe what it is? The first thing we're going to do is we're going to talk about percent composition. There's a formula here. If you're not comfortable with math, that looks kind of scary possibly. It's just going to get worse, so hopefully it doesn't look scary. But it really isn't. It's a simple idea that the math just goes along with that simple idea. Percent composition by mass just says of the total mass of your sample, what percent of it is from any given element. And so what this is saying is take the mass of the element you're interested in, divide by the total mass of your sample, multiply it by 100. That's the definition of finding a percentage, right? Take the part, divide by the whole, times 100. Just like you were finding if you were finding your grade on the exam. The total is 83.4. Divide the points you got by the points that were possible, times 100. It's the same thing. You can find the percent mass for every element that's in our compound or our sample. And of course, it has to add up to 100%. Because you have to account for everything that's in there, and they can't add up to more than 100%. This is our equation for mass percent. So this is just a simple example of it. We have a mineral called chalcopyrite. We have a chunk of it. Our sample of chalcopyrite weighs 3.67 grams. We do some fancy chemistry with it, and we know exactly how many grams of our mineral is copper, iron, and sulfur. And the problem is asking us to find the mass percent of each element. So let's start with copper. Copper is the first one listed. How am I going to find the mass percent of copper in my sample?
1.27 over 3.67.
Right. It's 1.27 grams. That's how much copper we had, divided by the total mass of our sample, 3.67 grams. When you put that into your calculator, don't forget to multiply that 100. Then times 100, and what do you get?
34.6049.
34.60%. Now we do the next same thing for iron. Iron, we have 1.12 grams of iron divided by 3.67 grams times 100 equals what?
30.5177.
30.51%. Now we have to do sulfur. There are two ways we can calculate sulfur. One is this way. What's the other way?
Add it up and then minus by 100.
Right. The three combined have to equal 100. And so whatever sulfur has to be to make this all add up to 100 is what it would be. So let's do it that way, because since we already did two examples like this, let's do sulfur the third way. So we just got 100% minus 34.60% minus 30.51% equals how much? 34.89%. This is sulfur, this was iron, and this was copper. And that's the end. I don't even care about sig figs at this point. We're past that. So I have 4 sig figs, and the answer should only have 3. So don't make percent composition more difficult than it has to be. It literally is just what percentage of your sample is each element. Take the mass of each element, divide by the total mass times 100. That's all there is to it. So remember, has to be 100%, which is what we used here. So here's another one. You have a different sample. All we know is that it's a copper compound, and the entire sample weighs 1.63%. So 1.63 grams, and we know it contains 1.30 grams of copper. It says the other element is oxygen. So it's telling us there are only two elements, and they must be copper and oxygen. What is the percent composition of the compound? There are multiple different ways you can go. You can attack this. You're going to get the same answer at the end. Which way do you want to go? Where did you want to start? I would just find the percent copper. That's the easiest thing. You're given two numbers, and so let's just use those two numbers that we're given. What is our percent copper?
79.75.
79.75?
Yes, sir.
Copper. So now we have our copper, we need our oxygen. Again, there are two ways we can find it. We can figure out just 100% minus that. That's probably the easiest way. And so 100% minus 79.75% equals 20.25% oxygen. What was the other way we could have done it? Exactly. So in this case, we weren't explicitly told the mass of our oxygen. In the other way, we had that number, so we could use the number we were given, or we could use a subtraction. In this case, then a mass of oxygen isn't directly given to us, but we know we have 1.63 grams total. Of it, 1.3 is copper. The other 0.33 must be oxygen. So then you could have done 0.33 divided by 1.63, and you again would have gotten 20.25%. So that is how the slide worked it out. They did it that way. Okay. That's mass percent, that's percent composition, same thing. Next thing we have to talk about are moles. Moles are a simple thing that that can be extremely confusing and complicated. Let me get rid of the word complicated. Confusing, yes. Complicated, no. Okay? Once they make sense, they make complete sense, and they're not hard at all. So, when we talk about atoms and molecules, they're very small, right? If I talk about this desk, and I'm trying to count how many atoms or molecules are in there, it's this astronomically large number. And so we need to have some way to connect the microscopic world with the real world. And to do that, we use what we call the mole. And 1 mole, M-O-L-E, is equal to 6.022 times 10 to the 23rd particles. 6.022 times 10 to the 23rd is what's called Avogadro's number. Is there anybody who used to work as a checker in a grocery store? I once had a student that did, and she thought it was funny because she knew avocado's number, the 4-digit code they have to type it in the register. This is Avogadro's number. This is not something you have to memorize, but it's another one of those things that you will memorize, that you'll use it so many times that it's 6.022 times 10 to the 23rd. It is on the cheat sheet, though. I believe it is literally the first thing on the cheat sheet. So if you don't memorize it, that's fine, but you're going to anyways. And when it says particles, particles can be anything that you want to count. Okay? A mole of carbon is 6.022 times 10 to the 23rd carbon atoms. A mole of hydrogen sulfide is 6.022 times 10 to the 23rd hydrogen sulfide molecules. So we've applied it to atoms. We've applied it to molecules. A mole of copper 1 oxide is 6.022 times 10 to the 23rd copper 1 oxide formula units. Remember, a formula unit is essentially a molecule, but technically ionic compounds don't have molecules, and so they're formula units. A mole of moles is also, you can use to count moles, the little fuzzy things, okay? You can use moles to count anything, okay? Anything at all. People, desks, periodic tables, planets, I don't care. If you can count it, you can use moles to count. Is anyone familiar with the comic XKCD? No. It's a nerd cartoon, okay? And the guy who writes it has this what if book. He goes through and we actually use scientific principles to figure out what if something were to happen. And one of them was, if you took 6.022 times 10 to the 23rd moles and put them in one place, what would happen? And it turns out that the gravity between them would pull them together, and then they would be about the size of the moon. That is how large a number, 6.022 times 10 to the 23rd is. It is a monstrous thing, okay? It's just, in real life, it doesn't seem that way because we're usually using it to count atoms and molecules, which are so small that when you have that many, it brings it into the tangible world. So like we said, it is what allows us to count microscopic things in the real world. The way this was figured out is Avogadro said, well, we look at the periodic table. He said carbon is 12. And we have these numbers down here, and those were atomic mass units. We said that is how much one atom of each element weighs. So he said, well, let me use this periodic table for double duty. Let's make these numbers also grams in the real world. And so he figured out how many carbon atoms does it take to weigh 12 grams. And it took 6.02 times 10 to the 23rd carbon atoms to do that. And so even though that seems an arbitrary number, it more or less is, but what it allows us to do is use all of these numbers down here as grams. So if we want to know how much a mole of oxygen weighs, it is 15.9994 grams. That's how much a mole of oxygen weighs. A mole of hydrogen weighs 1.00797 grams. It also allows us to go the opposite direction, which we'll be doing here. If you know how many grams of something you have, you can figure out how many moles you have, which in turn tells you exactly how many molecules of that substance you have. So it's really a pretty powerful thing. So this gives you an idea of how much a mole is of a lot of different things. So this is just chalk. So that's how much a mole of calcium carbonate is. Here we have table salt. The carbon is graphite, it's black, it's hard to see. There's some silicon, there's mercury in a little jar here, some sulfur, tin, aluminum, water. 18 milliliters is 1 mole of water. Okay? So it's not a lot, but it is definitely a usable amount. It's something that you can really relate to, something you can hold in your hand and deal with. So this is where people start to struggle with moles. So in this example, we're We're talking about hydrogen sulfide. If we're talking about hydrogen sulfide. That thing as a whole, is that a molecule or an atom? It's a molecule, right? There are atoms that make up that molecule. And so what this is saying, when it says how many sulfur atoms are in 1 mole of hydrogen sulfide, it's saying we have 1 mole of hydrogen sulfide molecules. Then it's asking, okay, if we have that many hydrogen sulfide molecules, how many sulfur atoms are included in those? A mole is an easy thing to do, okay? People make it more difficult than it has to be. You can use moles exactly like you would use dozen. So if I asked you to count in dozens, you can all do that. If I said you had 36 molecules, how many dozen is that? 3. You just did that, right? A mole is the same exact thing. It's just instead of dealing with an easy number 12, you're dealing with 6.022 times 10 to the 23rd. So let's do this first in dozens. So let's imagine it says how many sulfur atoms are in 1 dozen hydrogen sulfide molecules. To figure that out, you have to think in each molecule, how many sulfur atoms are there?
1.
There's 1. In every molecule, there is 1 sulfur atom. 1 molecule is 1 sulfur atom. And so you have the same number of sulfur atoms as you have molecules. Because for every 1 molecule, you have 1 atom. And so if you have a dozen molecules, you have a dozen sulfur atoms. If you have 1 mole, 6.022 times 10 to the 23rd molecules, you're going to have 1 mole of sulfur atoms. You just take the number of moles of molecules, multiply it by the subscript on that element. In this case, it's 1, and so it doesn't change. For hydrogen, though, let's say we have a dozen molecules. How many hydrogen atoms do we have? 24. 2 dozen. We have 1 dozen molecules. 1 dozen times 2 is 2 dozen. That's all there is to it. So if we have 1 mole of molecules, we have 2 moles of hydrogen atoms. So this is what we were just saying, but these numbers are grams. When we read this now, it is called the molar mass, meaning the mass that 1 mole contains or has. Okay, it's the mass of 1 mole, and the unit is going to be grams per mole, which is literally what it means. It's how many grams something weighs per mole that you have. For every mole that you have, it weighs that much. The molar mass of oxygen is 16 grams per mole. If you want to find the molar mass of a molecule, you're going to do it the same exact way we found the molecular weight. It's just at the end, instead of putting AMU for atomic mass units, you're just going to put grams per mole. So carbon dioxide is 1 carbon. That carbon weighs that much. 2 oxygens, so oxygen is 16, so 2 times 16. Added together, you get 44.01 grams per mole. That is the molar mass of carbon dioxide. 1 mole of carbon dioxide weighs 44.01 grams. So, hydrogen. What's the atomic mass of hydrogen? If you want to round it, you can just round it to an even number. 1. What's the molar mass of hydrogen? 1 gram per mole. Here's 1 AMU, 1 gram per mole. Oxygen is 16, sodium is 23, 23. Let's do the calcium chloride. So what is the mass of calcium?
40.
40, and then there are 1 of them, so that's 40. Chlorine is 35.45. How many chlorines are in that calcium chloride? 2. There's 1 chlorine per chlorate, but there's 2 chlorines. So 2 times 1 is 2. That comes out to be, is it 35.45 or 34.45?
35.
Oh, that's right. So that comes out to be 71. Oxygen is 16. How many oxygens do we have? 6. 2 times 3 is 6. I can't do 16. Well, I don't want to do 16 times 6.
96.
Thank you. 96. Just add them together. We've got 7, 13, 207.
Yes.
207 grams per mole. That's the molar mass. The atomic mass of the molecular weight would be 207 AMUs. Water is 16 plus 2 is 18. Sodium chloride 23 plus 35.45. Is there anyone that's not comfortable doing that? So now I'm going to make you think. And this is what everybody hates doing. Everybody likes plugging in numbers and getting an answer. They don't like thinking. If I have a mole of copper and a mole of gold, which one has more atoms? They're equal. A mole says I have 6.022 times 10 to the 23rd atoms. It doesn't matter whether it's copper or gold, I have the same number of both. Think of it as a dozen. You can always go back to that dozen example. If I have a dozen copper atoms and a dozen gold atoms, and the question asks me which one do I have more atoms of, it's neither. I have 12 of both. That is what this is saying. A mole is a mole regardless of what the element is, regardless of the mass of each atom. Now, what if I have a gram of copper and a gram of gold? Which one has more atoms? Why copper?
Because copper weighs less, so you need more atoms to weigh the same amount.
Correct. Correct. What she said was that we know we have a gram of each. A copper atom weighs 63.5. Gold weighs almost 200. So every gold atom is much heavier than a copper one. So it's going to take a lot more of the copper ones, which are lighter, to add up to your 1 gram. Right? If I said I needed 100 pounds of bricks or feathers, is it going to take more bricks or more feathers to equal 100 pounds? More feathers. The lighter one it takes more of to equal the same mass. So 1 gram of copper is going to have more atoms. Now we're going to do this mathematically. We need to be able to go from a number, take a number of moles, go to grams. We need to be able to go from grams to moles as well. So the first one wants us to convert 10 grams of carbon dioxide to moles. We're going to use dimensional analysis to do this. So I have 10 grams of CO2. Now, ignoring that, imagining that's not up there, you don't know how to do this conversion yet. Based on what you know about dimensional analysis, what unit has to go there? Grams of CO2. That fact will always hold. That unit has to go there. So now what this is, remember this is a conversion factor. You need two things that are equal to each other. And the conversion factor we're going to use is that 1 mole of carbon dioxide weighs 44.01 grams. 1 mole of carbon dioxide weighs 44.01 grams. It's just the molar mass. Now, we've canceled our grams of CO2. Top right corner, we have moles of CO2. We're done. We did it. We just have to put it into our calculator. And when you do it, you get 0.227. And the unit is moles of CO2. And we abbreviate mole, MOL. Yes, it only saves 1 letter, but when you write it 100 times, it saves you 100 letters. Okay? So you can write it with or without the E. Now we're going to go the other direction. Let's say we have 0.50 moles of CO2. We need to go to grams. What's my unit down here on the bottom? Moles of CO2. 1 mole of CO2 is going to equal 44.01 grams CO2. Again, it's set up correctly. All you have to do is put it in your calculator.
22.005.
Yes. So, it's a one-step conversion, and your conversion factor is 1 mole equals the molar mass. You have to figure out what that molar mass is unless it's given to you. So 1 mole for CO2 equals 44.01 grams. Okay. Yes?
That's the molar mass of CO2, 44.0.
44.01. That's the molar mass of CO2. So some people like to turn this into a set rule. And so what you can do is you have X grams of something. It's the molecular weight grams is 1 mole. Or you can do it the other way. If you have X moles, 1 mole is going to equal the molecular weight grams. Where the number is the molecular weight, and then the unit is grams. So if that's helpful to you, you're welcome to do that, but you're not going to have that on your cheat sheet or anything like that. And so if you're going to use this, it's got to be stuck up here. So here we converted 10 grams of oxygen to moles. This was 10 grams of CO2. That is 10 grams of oxygen. The only thing that's going to change is that number, because oxygen has a different molar mass. You notice, remember, it says O2, and so the molar mass is going to be 32. There's 2 oxygens there. So each one's 16, so O2 is 32. Now we can go between moles and particles. We're going between grams and moles. We can go between moles and particles to moles. Again, it's going to be dimensional analysis. We're just going to have to add a step. And for that step, this is our conversion factor. 1 mole is 6.022 times 10 to the 23rd particles, and you just replace the word particles with whatever it is you're counting, whether it be molecules or atoms or whatever it is that you're dealing with. Down here at the bottom, there's a flow chart showing you how to go between them. And so if you want to go from mass in grams to moles, or moles to grams, it's telling you you need to use the molar mass to go between them. To go between moles in formula units or molecules, you use Avogadro's number. And then if the question is asking you how many specific atoms of one element are in that mole of molecules, then you'll use the subscripts in your chemical formula, like the H2 or the H2S, to find the number of atoms. So our first one is how many CO2 molecules are in a 100-gram sample of CO2? I am just going to repurpose this. Erase my decimal there. So 100 grams of CO2 is for, yeah, go to moles, grams to moles, just like we did before. And now we need to go from moles to molecules. And so I'm going to add a step on. I have to have moles of CO2, and I'm trying to get the molecules. So I'm going to put molecules CO2 up there. What numbers are going to go here?
Avogadro's numbers up top.
Right. 1 mole is equal to Avogadro's number of molecules. That is our conversion factor. And so one of them needs to be on top, one of them needs to be on the bottom. In this case, we were going from moles to molecules, and so moles has to be on the bottom. If we go the other direction, and we need to go from molecules to moles, we're just going to flip our conversion factor. So if you put that in your calculator,
1.368 times 10 to the 24.
it's a very large number, but you would expect it to be a very large number, right? 100 grams is quite a bit. And we know that molecules are tiny, tiny, tiny. So if they have to add up to 100 grams, you're going to have a lot of them. So that makes sense. Now, the next question says, how many carbon atoms are in a 100-gram sample of CO2? I ran out of room. What I'm going to do is I'm going to copy this part down here. So imagine this is that, and we're going to continue on from there. So it's not on there twice, this is just showing you where it connects. Okay? So I have molecule CO2, and so molecule CO2 has to go down there. I'm trying to get to atoms of carbon. What numbers can we put here?
1 molecule, 1 carbon.
Correct. Every 1 molecule of carbon dioxide has 1 atom of carbon, because it's CO2. There's only 1 carbon here. And so that's not going to change my answer at all, because I multiply it by 1, I divide them by 1, nothing happens. What about the oxygen, though?
There's 2 atoms of oxygen for 1 CO2 molecule.
Correct. Now 1 molecule of CO2 is 2 atoms of oxygen. Now that's going to double my answer. So it's going to be an even larger number. It comes out to be 2.74 times 10 to the 24th. So you can do it logically. You can say, well, I have this many molecules, and there's 2 atoms per molecule, to multiply my answer by 2. Or you can do it with your dimensional analysis. It's the same exact thing, it's just, instead of logic, you're using your units to guide you. The moles to grams, people get fairly easily. People, once they do some problems with it, they get it. Where I see people struggle over and over and over again is when they go to molecules and atoms, particularly from the molecules to the atoms. It's such a simple thing, but they overthink it. Okay? Find which way works for you and go with it. So here we're going to go the other direction. Now we're starting with molecules, and it says what mass of magnesium chloride contains 6.022 times 10 to the 23rd chloride ions. So I only have one number to start with. That's where I have to start. So I have my unit. That has to go down here. Now you're going to have to think a little bit ahead of yourself and work out a roadmap to get from chloride ions to mass of magnesium chloride. Where do you think you want to go next? What I'll point out is currently we are in chloride. Ultimately, we need to get to magnesium chloride. Yeah.
We have to know that there's 2 chlorine atoms in that one magnesium chloride molecule.
Correct. If we can get into molecules of magnesium chloride, then we're okay. It's that first step that people really struggle with. So in magnesium chloride, there are 2 chlorines. There are 2 chlorines per magnesium chloride. So there are 2 chlorides per 1 magnesium chloride, and we'll call it a molecule, even though we know it's technically not really a molecule. So 1 magnesium chloride molecule contains 2 chloride ions. Now I've got magnesium chloride molecules. Where do you want to go next? Let's go to moles. We know how to go from molecules to moles. Once we're at moles, then we know how to get from moles to grams, and that's what we're trying to get. So we see the finish line. So we've got molecules. Let's go to moles of magnesium chloride. Now what numbers are going to go here? 1 mole of magnesium chloride.
Avogadro's number on the bottom.
Right. One mole of magnesium chloride contains 6.022 times 10 to the 23rd magnesium chloride molecules. Avogadro's number is your conversion factor between particles, whether it be molecules or atoms, and a mole. If you need to go from molecules to moles, there are no other options. 1 mole equals 6.022 times 10 to the 23rd of whatever it is you're dealing with. Now I have moles of magnesium chloride. Now I can go to grams of magnesium chloride. What number you want to put down here?
1 mole.
1 mole of magnesium chloride weighs how much? And you have to calculate that. So 2 chlorines is 71 plus 24 is 95.3. That's the molar mass of magnesium chloride. It's now set up in the end. This is 47.60 grams of magnesium chloride. So we went from atoms, essentially, in this case it was ions, because it was an ionic compound. But we went from atoms to molecules, to moles of molecules, to grams. On a whole, it looks big, but you need to break it down one step at a time. If I am here, where can I go from there? And once you're there, figure out where can I go? Always making sure that you're moving at least in the right direction. Okay. You'll do a few of these. If you struggle with them, please let me know. Don't say, I don't know how to do this, I can't do it, and then not figure it out. Okay, we'll work it out. You just got to let me know that you're struggling with it. Next thing we're going to do is calculate empirical formulas. An empirical formula is a molecular formula, just like we have dealt with before. It's just a formula, but it's where the subscripts are the simplest ratio. Remember with our ionic compounds we said that if they can be simplified, they have to be simplified? That is telling us that for an ionic compound, what we write down has to be the empirical formula. For our molecular compounds, we said you don't simplify them. But if they can be simplified, what that means is that there's an empirical formula, which is the simplified version, and then there's the molecular formula, which is not. So an empirical formula is just the simplified version of a formula. Whereas the molecular formula tells us the actual number of atoms in a molecule or a compound. So for example, this is going to be coming up, but benzene is C6H6. That is a molecular formula. That tells us in every benzene molecule there are 6 carbons and 6 hydrogens. That's what differentiates that from all of the other compounds that have carbon and hydrogen. In this case, there are 6 and 6. But that can be simplified. If you simplify that, what does it simplify to?
CH.
Just CH. C1H1, but we don't write ones, and so it's simplified to CH. So that's our empirical formula, right? But there are literally an infinite number of molecules that have that empirical formula. But there's only one molecule that has that molecular formula. So here is our benzene. This is C2H2. What does C2H2 simplify to? CH. And so the ratio between the carbon and the hydrogen is the same in both of these. For every one carbon, there is one hydrogen. The empirical formula is telling us that ratio, completely ignoring how many are in each individual molecule. So the empirical formula for both is CH. They have the same empirical formula, but they have different molecular formulas. And because they have different molecular formulas, they are different molecules. They are very different molecules. What is the empirical formula of hydrogen peroxide, H2O2? HO. What is the empirical formula of water, H2O?
H2O.
H2O. It cannot be simplified, and so it just stays the same. And so the molecular formula and the empirical formula are the same. In this case, they have different empirical formulas and different molecular formulas, so certainly they are different compounds. So here is a number of compounds. They all have very different molecular formulas. They are different compounds, but they have the same empirical formula. C5H10, C6H12, C2H4. They all simplify to CH2, hydrogen sulfide, like our water, H2O. The molecular formula is the same as the empirical formula. If you see, we're going to calculate these. Just remember, it is possible for the molecular formula to be the same as the empirical formula. If you calculate that's the case, that doesn't mean you did something wrong. calcium chloride, that's an ionic compound. By definition, the formula that we write is the empirical formula. Because we said if it can be simplified, it has to be simplified. So you would never write anything for an ionic compound that was not in empirical form. So when we calculate empirical formulas, we are going to start with our percent composition, our mass percent that we started the lecture with. We're going to come back to our chalcopyrite. And we knew that this was our percent composition. And the reason we're going to do this is because if you have a sample of a mineral, and you don't know what it is, and you put it into an instrument, or you have some tests that you're going to do on it, it is not going to tell you the formula for that compound. What it's capable of doing, what it's going to tell you, is what percent of each element is in there. And you are going to have to figure out what the formula is. Okay? So, like we've seen before on things like this, we have some instructions. They seem pretty daunting, but they're not. Okay? So once we work through the first example, it will be okay. So the first problem we're going to do is we have 100 grams of chalcopyrite. Okay? If we have 100 grams, that means the percentages become grams, right? If I have 100 grams and 34.9% of that 100 is sulfur, it's 34.9 grams of sulfur. So, rule in step number 1 is assume any size sample that you want. If you're given percentages, you can assume any size sample that you want, but you do not want to assume anything other than 100. Assume 100 grams. That makes the math so much easier, because then the percentages just become grams. Erase the percent, write a G. Okay? So now we have grams of iron, copper, and sulfur. Next thing we need to do is convert the grams of each to moles of each. So here, we've divided the masses by the molar masses and gotten moles. We'll do examples on the board here, but we're just going to quick go through the first one. So we found the moles of each. Next step is we need to get all of these moles to whole numbers. Because these numbers here are going to end up our subscripts in our formula. And we can't put partial numbers, we can't put decimals in our subscript. We have to have whole numbers. So what we're going to do is we're going to look at these three numbers, pick out the smallest one. What is the smallest one? 0.5444, and divide all three of them by that number. So 0.5461 divided by 0.5444. And 0.5444 divided by 0.5444, 1.088 divided by 0.544. When you do that, you're going to get new numbers. At that point, hopefully, those will be our subscripts. When you do that, our iron comes out to be 1.003. Copper is exactly 1, because if you divide any number by itself, you get 1. Sulfur is 1.999. If you look at that number, does that look like it's supposed to be a whole number? What I mean, is it really, really close to a whole number?
Yeah.
Yes. What about that one?
Yes.
Yes. Keep in mind that when you made these percentages back a while ago, you rounded. And so because you rounded when you made these percentages, you can't expect these numbers to come out exactly dead on. And also, these numbers were due to experiments that you did in the lab. And you know that if you do measurements in the lab, there's going to be error. And so, you can't expect these numbers to come out exactly even. If you look at a number and it's very, very, very close to a whole number, you round it. If it is not really close, and when I say really close, I'm going to say within 0.1. 0.1 is going to be our rule. If it is further away than 0.1 from a whole number, we're going to have to do something else to it. You can't round that. But in this case, they're all very close. And so these numbers become our subscripts. We have Fe1, copper 1, sulfur 2. Okay? We're going to do more examples. So here's one that we're going to do. We have another mineral called cobalt. We know the percent composition is 66.5% copper, 33.5% sulfur. Our first step was to convert percents into grams. How did we do that?
Just change it.
We just changed it. We said, well, we can pick any size sample that we want, so we're going to pick 100 grams, and so our percentages just become grams. So I've got 66.5 grams of copper, and I have 33.5 grams of sulfur. What was our next step? We need to go from grams to moles. So I need to go from grams of copper to moles of copper. 1 mole of copper weighs how much?
63.5.
63.54 or 5.
We'll just go 63.6. So how many moles of copper do I have?
Well, I got 1.04649.
Okay. 1.06. Is that what you said?
1 point, yeah.
Okay.
1.0.
Mole of copper. 1 mole of sulfur weighs 32.
Yes.
32 grams sulfur. What does that come out to be?
$1.045 basically.
1.05 moles of sulfur. No.
Divide by the.
Divide by the smallest one. This is a step a lot of people like to skip. What people like to do is say, well, that's close to 1, round it to 1. That's close to 1, round it to 1. I'm done. In this case, that's where we're going to end up. But in a lot of cases, that's not how it's going to end up. People end up just rounding and they get the completely wrong answer. Divide them both by the smallest number. That one is exactly 1. What does this one come out to be?
1.009.
1.01. So, can we round that first one? The top one?
Yes.
Yes. I say if it's within 0.1, you can round. We're within 0.01, and so we can round it. So that becomes, it's approximately 1. And so we now have whole numbers for both, so we're finished. We just have to write our formula. So our formula is copper, what's my subscript? 1, because that's a 1. Sulfur, 1, they're both 1s. I don't write 1s, so it's just CUS. So that's everything's worked out on that slide. Another one. We've got shadokite. Shadokite has 4 elements in it. It's going to be the same process. It's not necessarily more difficult, it's just more work. So first step was to make our percentages grams. So I'm going to have 48.43 grams of copper, 17.12 grams of silicon, 34.14 oxygen, 0.031 hydrogen. I need to convert all of them to moles. Copper was 63.5
Yes.
grams. Copper, 1 mole. Copper. So
28.09.
we'll just go 28. Oxygen 16. For oxygen and hydrogen, because we're just dealing with oxygen and hydrogen, not oxygen molecules or hydrogen molecules, it's not O2, it's not H2, and so it's just 1 gram and 16. You don't have to multiply it by 2 to get that mass. So what's my moles of copper? .70.
Six.
That's 6. So what about my silicon?
0.693.
0.693.
0.93. So
So
it's
6.1.
basically 6.1.
We'll go 6.1. What about oxygen?
2.1.
2.1. And hydrogen?
0.31.
0.31. Are we finished? We just round them?
No, divided
No.
by the smallest.
Divide by the smallest one. What is my smallest one?
0.31.
0.31. That is 1. What do the other ones come out to be?
Big numbers.
What's top?
That,
2.45.
2.45. One
1.97.
0.97.
No, it's 1.97.
1.97. 6 point. Is that right?
6.7.
Is this 2.1 correct? Double check that please for me.
Yes, sir, it is.
So if we look at these, in this case, there are some that we said we cannot round. This one's okay, that one's okay, that one, and that one are not okay. So what we're going to do is we have to multiply these to get them to a whole number. And so if we look at that top one, what's a clean number that is close to? 2.5. What can you multiply 2.5 by to get a whole number? 2. If that doesn't immediately jump into your head, you can always do process of elimination. If I take 2.5, multiply it by 2, what do I get? I get 5. In some cases, you multiply it by 2 and it still won't be a whole number. So then you say, what if I multiply by 3? What if I multiply by 4? Okay? Just keep going until you find a number that you do get a whole number. If I'm going to multiply that by 2 to get a whole number, I have to multiply all of them by 2